My name is Dvir. I work at CEVA as a compiler. And today I'll talk about a variety of variants. Okay, let's start with some motivation. Who doesn't like state machines? Connecting to previous talk, let's take a look on the scenario of connecting to a server. So typically, a client will have several states in its life. Disconnected, connecting, connected, and sometimes interrupted. There are transitions between states, and each state has some relevant data for this specific state. Like where when we are interrupted, we would like to know the time that the interruption occurred. So the next solution is to implement this machine is to make one object which has some enum for the state and all the data that we need in all the states as members of the object. Okay, what's wrong with that? So let's see, for instance, a transition between states when there is an interruption of the connection. So then we need to know which state we are at. If we're still haven't connected, we simply go to a disconnected state. If we are already being connected, then we take the time, notify someone that we've been interrupted, start some timer to try to reconnect. But still, on each state, we have access to the data members that are not relevant for this state. So, for example, we could here accidentally touch the timer, and of course, all this code can be in different functions that don't always see each other, and we wouldn't want this to happen. Another thing, when we're disconnecting, we need to worry. Maybe we had the timer on and we need to kill it. Okay, so because we have access to the timer here, no matter what state we are, we need to be worried about what to do with it. So to conclude, data is accessible where it shouldn't be. We can't use II ADMs because the objects are alive at all times. And what we would like to achieve is to simply make illegal states, like accessing data we shouldn't be accessing, to make it illegal to compile. Let's take a short break from the topic of the talk to talk about generally about types. So Modiin from Blizzard made an excellent talk called Using Types Effectively on CVPCon 2016. Has anyone seen this talk? Okay. So I borrowed some slides from this talk with permission from Ben, so you don't need to sneeze.
He's a nice guy.
Yes. very much. So let's play a game. I'll show you a type, and I want you to tell me how many values this type has. Okay? First level, how many values can this type have?
Two.
Two values, right? True and false. This 256. This one?
One. None.
Some say one, some say none. And
some say depending on the word size of an integer.
okay. So the answer we seek is 0. Okay, you can't in C++ at least create any object of type void, right?
Yeah.
So there are no members of this type
We'll discuss it later.
until void p.
No, you can't, but because it has only one value, so you don't need. It's more philosophical, but it's one, it's not 0. But
Okay.
I'm with the 0.
we can discuss it some other time.
You can press void to somebody.
I have a class. It's part of another talk I'm working.
So maybe talk to Ben.
Some other time.
Okay. And this type.
With the 7.
256. 3. Okay, again, the number of legal values we can create of this type are 3. It's right that the underneath representation has more values, but other than these 3, the other values are not part of the type.
There are code bases. So a code base, not just a code base, an official game, AAA game, which had all enums had only unknown -1. It read all the values from XML files, configuration files, and then just use the enums as a type. So a function can be marked as receiving a type, and the compiler can check it, but you still could assign any value which was not in the code to it.
Okay, that's another thing. The telling me enum has to be like a strong type for an integer.
Yeah, exactly. So it still
Okay,
can
that's
receive
maybe a different.
completely legal, valid, and defined behavior to assign other values here. So
Not this one. Not this one.
why
I
not?
don't think.
If you assign
it's
4
illegal,
to it
it's
or
not
5 to it, it's completely legal and defined
In
behavior.
C, I'm not sure.
No, in C++.
It's
not
no
in
problem.
class.
Even if it was
a member of this,
Yeah, class.
even
even if it was enum class, you could have casted it and it would have been fine. Cast is
I
completely
think we're
valid.
going to change that in C++. Proposal about
We'll see about that.
when the break is
Okay, finally, how many values does this type have?
Infinite. Key has.
Infinite? Right. Okay, depends on T. This type will have as much values as T. Okay. Congratulations, you got through level 1. Okay, so the concept Ben and I would like to talk about is algebraic data types. So it's a whole theory of looking at types through just the number of values they can hold. So for this theory, bool and enum of two what? Two values. Thank you. They're equivalent. And the theory is actually about how to use types to express relationships in a program. Let's continue to level 2. How many types? How many values?
512.
500.
Correct. This one.
Same, 500.
Correct. 74.
8.
You're good. This one.
2 times view types.
Correct. So what we've seen in this level is product type. Okay. The name is clear. The number of values the type has is the multiply of all the types it contains. Okay, so struct and tuple are two classic examples. Okay, let's pause the game, and we'll be back to it later. Okay, so now let's finally start to talk about std variant. So a little introduction. We can declare a variant of a specific list of types, and then we can assign each one of these types to the variant. After we assign, we can get it using the std get function, giving it the required type. If we try to get a type and it's currently not the type the variant holds, then an exception will be thrown. Type bad variant access. If we try to get type which we did declare in the variant declaration, then it won't compile. And if we assign a value of a different type, then we can get the type we just assigned. Okay, another useful function, getIf. It won't throw an exception in case we give a type which it doesn't hold currently. It will just return null, and then we can check it. Okay, notice that here you need to give a pointer to the variant instead of a reference. I think it's left over from Boost. Or maybe to make it more clear in the code. Okay. It wouldn't be too convenient if we needed to use all these getIfs.
Maybe it's to solve
if we have a long list of types. Okay, assume we have a variant of like 10 types. We wouldn't want to getIf string, then this, getIf int, something else, etc. So this is why we have std visit. Okay, we give std visit something callable, which, for example, it can be a function object, which is an object which has operator parentheses, the call operator, and std visit will simply call the correct overload of the call operator with the type that the variant currently holds. Okay, so if we had an int, and inside we call the first overload, otherwise the second. So
if there's no overload, it will accept.
It won't compile if there is no overload for all the types.
Oh.
So a variant can call only, it can be either an int or a string, not
right. It can be either an int or a string at each time.
Or none of them. obviously.
No.
Context construction. Unless you have
It's
to
The definition of the
first
first
line.
No, we don't talk about
It won't be if the first type is default constructible, then also the variant will be, and
first type.
it will be a default constructed to the first type. Otherwise, it won't be default constructible. There is a special type called the std monostate, which you can put as the first alternative to make it default constructible if none of your types offer.
Can it change the type and the runtime, or
No, the set of types are fixed compiled.
I don't need the list of the types, but can I?
Yes, as we saw earlier, you can assign a string to what was before it.
it. It feels like dynamically typed on the closed set, like JavaScript, MATLAB.
Yes, otherwise it wouldn't be useful.
I don't understand why it's useful.
It's called the discriminated union.
We'll
It's like
go back
a
to the example.
You laugh miserable when you're going to maintaining the
constexpr.
No.
marble that you don't know what it is.
Polymorphic lambda.
We'll see. I think we'll see that in a few slides. A little bit of history. It started again as a Boost library by two guys. One of them is Israeli.
I couldn't. He doesn't.
Tap on shoulder.
I'm trying to get him to come.
All right. Okay. Lucky he's not here today.
Yeah.
Released in 2004 and became part of the standard from C++ 17. The interface is almost the same, but has some changes, as we'll see later. There are many implementations of the concept of variant, other than the standard library. There's Boost, Qt, and many others. So if you don't want to use C++ 17 or Boost, you can choose from this.
I think there are also backports already, or at least.
Yes, this is backport of the standard to C++. Let's continue the game. Do everyone know STD optional? Okay. How much?
No.
57.
57, right? Either a character or an empty state, which is an additional value of the type. And from what we just saw,
257.
258.
258, right? Everyone understands why? This type? Correct. So optional variants are two examples for sum types. Okay, sum types, we sum the number of values of each component. Okay, again, we'll continue the game later. So going back to what we've started with, the connection state machine. Now we'll implement it using STD variant. We collect the members, the data, relevant data for each state in its own object, which will represent the state. And then the state will simply be a variant over all the different states. Okay, and other members like the address are probably relevant to all the states, so we keep them separate. Let's see how we use it. So now, disconnect. If we were in an interrupted state and timer was on, our AII kicks in and destroys the previous state, and the timer will be destroyed and hopefully cleaned. And interrupt, we use FTD visit. Depending on the current state, the correct overload of the call operator will be called. Okay, here we pass this to the function object, so we can call some member function later on.
Just a sec. Question?
So which state is a separate type?
Yes, state is a type, which is a variant of the different state objects.
So what do you gain from the variant? You could just implement that as it was before, because you could implement each state as a struct as you did before. What you gain from using variant?
Yes, but what would we represent?
They're
You're
mutually
saying
We're
exclusive.
using
Using
enum
runtime.
for the
enum.
They're mutually exclusive at runtime. No two can exist at the same time.
Yeah, you cannot.
So you get
cannot
the
mix.
destruction. You get you can't access accidentally something you shouldn't.
Okay, so notice here we have the same code on two branches. We can use a template call operator to unify them. And here what will happen is if the type will not be one of the specific overloads, then we'll call the template version. Okay, with whatever type it is.
What is this label encapsulation? I mean, this event structure probably needs to be defined with all state types. If it is to do anything useful.
This struct,
Can expose all these setters.
usually it's okay. Again, since it's template, we can't put it inside the function. We can't put a template function inside another function. So we need to put it outside. But usually it's still inside the big struct connection. So it's a substruct of.
It can access the state through an API or something.
And
It doesn't have to access
the
the
constructor
return
gets
number.
the connection, so it has access to everything.
Yes, and you pass
I would say that this
the connection here. So.
operation. You don't-
Yeah, well, you can have a disconnect method.
Okay, one other thing I forgot to mention is that you can also return values from the call operators, and here we just return the next state and then assign it to the current state. Okay, so it's very convenient to make the state transition like this. Okay, so let's dig a little deeper into the visitation concept. Okay, so defining a struct like this for every functionality we want to implement is a little bit overhead. So I think Victoria Romero came with this idea first. You can pass a list of lambdas to to some wrapper object called overload, and eventually this will be translated to a similar function object as we saw before. But you don't need to define.
Very testable.
Yes.
Define it.
Speaking of,
Because you can.
By the way, if overload is an object, maybe it would be best to.
No, overload is a function that creates an.
Okay.
best to create it outside and then.
Okay,
I'm worried about it. I thought.
I have a slide how it's implemented, but it's less important for the sake of this talk. Once it's implemented in some header, you can forget about it and simply stick it as almost as a keyword. Okay, again, we have generic lambdas from C++14, which are basically the same as template functions. So it's almost like a switch statement now. Okay, you have different cases and default cases. Okay, I think it's very succinct.
You can put it in the C4GC. So just open API.
Yeah, no, I think there's actually proposal.
The proposal for overload in C++.
Okay, this is the implementation, very short in C++17. I won't dig too deep into this. You can check the slides later on. In C++11, it's also implementable. A little bit longer. Another way to do the visitation is using constexpr. If you are in C++17, does anyone doesn't know what is constexpr? Okay, that's like an if statement in compile time. So just pass one function and then start to ask questions about the type of the parameter you got. So if it's of the same type as connected, the this, connection interrupted, and default.
But it's not really one function.
No, it's one function.
You write something that looks like one function, but it's polymorphic, so it's a template really. And the if constexpr actually produces multiple different functions.
Right?
Yes, for every call operation.
But it's not selectable for the variant. The variant always calls
The same one.
the same one. In the previous switch case, you had different overloads, and the std visit could have chosen the right one according to the type of the variant. Here you don't have it because nothing in the signature
No, of
here.
course you do.
Nothing in the no. This is the catch-all. Nothing in the signature here states the key.
Yes, it's implicit. The compiler will generate multiple
Compiler
instances
does that.
of this function. It will get cloned however many states you actually have. But that's a good thing.
It would get
It's not
close.
really, it's not really if you write a single function, but it's actually exactly the number. You have multiple instances.
It will get cloned because of the visit or because of the constexpr. So you only have three here. When you get to the else, return.
It's both.
How can it? It's generated before you call the std visit. So
It's
how
a
can
template that lambda which is going to get called with multiple types. So that's one clone. And each one of these might be cloned again for each branch of the if context.
So you can't.
If you get it.
So you can't assign it to some kind of an auto lambda outside of the std visit and then call it because it wouldn't compile. No.
If constexpr is compile time.
Not about the constexpr. The entire lambda, which is a generic lambda. It's not one. It's a generic lambda. Can you assign the entire thing that is inside the std visit into a variable outside of the std visit and then just send the variable?
No. The variable is an output.
Because it's not a single
because it's a generic lambda, regardless of the constexpr.
No, because of the constexpr, it doesn't evaluate a single object.
Just like a template function doesn't evaluate a single object.
If I had a type there, instead of const auto state, just a type, never mind what's the type, and then you add the if constexpr inside. Could you have assigned it to a variable?
Yes.
I'm sorry,
Yes, you could. Auto A equals this.
exactly. So the constexpr doesn't create multiple functions because you can assign it to a single variable.
That's
what creates.
Well, I'm sorry, I'm detracting from your. Let's discuss it later, maybe.
It's the use inside visitation. But the question is, if you don't have your fancy context, or if you just if, I think it would work exactly the same because STD same evaluates to some constant value.
Yes, this function will be instantiated multiple times according to the different types of the variables.
It's strictly required. It will work exactly the same even if you don't have it.
Don't have what?
You don't have to use
Just simple if.
if context. You can use simple if, but
And then it's just the default.
this is just what we wanted to avoid with this.
If sometimes one of the branches of the if won't be compiled if you use regular if. That's why you should sometimes use if context. So
But it doesn't create a new
if one of the
function.
if one of the branches are not legal and you want to avoid using it for some kind of type, then you could use if context.
No, I think this is exactly the example. Notify interrupted doesn't exist if the state is connected. So in this case, you have to use the if context, otherwise
Right,
it's not
but
going to
it's only duplicated because of the generic function, not because of the
but it
type.
depends on the argument of the state. The using statement depends on the state variable.
Okay, I
So-
suggest we'll have a talk on context for
Yeah.
Okay, I'm summing now.
And generic
Yeah.
Personally, I use the overload
That's
way and
more popular.
I think it's most important. Okay. Let's see another use case. JSON parsing. Okay, for anyone who doesn't know, JSON is protocol which mostly uses on networking, but also
Serialization.
serialization. Okay, it's a simple textual representation where you have keys and values, and the value can be of this list type: null, number, string, boolean, array, which is a list of values, or an object which is can have values inside. Okay, so this situation, we would like to make a type to represent a JSON data type. I think it calls for something like a variant. Okay, where you have several options of the actual type. Okay, so let's try to use that variant. We list all the possible types, and for an array, we would simply would like to use a vector of JSON values. The problem is we're now defining what the JSON value is, so we can't do that. Similarly with object. Like any problem in computer science, let's all at the level of indirection and use pointers. Okay, we forward declare the JSON array and JSON object, and then instead of using the types themselves, we are using a pointer to the type. And the types themselves array and object are shown here. Okay, I'll talk in a minute why I need this make vector function. Let's see how we construct. This is the JSON example I took from Wikipedia. And to construct a JSON value which represents this JSON file. So we had unique pointers, so we want to use make unique. Problem is, make unique doesn't work nicely with initialize lists. Actually, any variant template doesn't work well with initialize list, so we need to specifically declare the type of each member of the list. And this is also the reason why I needed this make vector function. Okay, because I'm using unique pointers which are not copyable, then again, initialize the list has to be copyable. So I can't use initialize list constructors. So I'm using variant templates and but this is not okay. It's an implementation detail. So this is how we are constructing this JSON. And to use it, let's see, for example, an output operator. Again, I'm using the overload technique. But now let's say I want to deal with an array. I get a unique pointer. Now I need to ask myself, maybe this pointer could be null, and what does it mean when it's null? Okay, it isn't clear. And likewise, all of my accesses are with pointer semantics. So it's a little bit inconvenient. Boost has a nice solution for this. Instead of using unique pointer, you use Boost recursive wrapper. Now you can, recursive wrapper is copyable, so you can use initialize list constructors. Since you're using initialize list, it looks much nicer, almost one-to-one with the textual representation. Another tiny glitch, you have to use string literals, otherwise the constexpr star or constexpr array would map to the bool type, not the string. Okay, again, if you assign string literal to this type, you will get a bool, not a string. So I'm telling it I want.
That's what people love C++.
And there is a perfect explanation of why it happens.
Okay. So and likewise with visitation, Boost the recursive wrapper makes it that the signature of the handler you don't need to even mention. If you mention you're using the Boost recursive wrapper, it will be casted to the underlying type for you. Okay, so simply get a type and use it like any other type. Questions? Okay, the reason that the standard didn't took this path is that they didn't want variants to allocate memory without you telling it use the unique pointer explicitly. So that's why it didn't enter the standard.
That's the difference between boost variant and the
Yes,
standard
it's
variant. Boost variant
the biggest difference.
Boost is always allocating on heap, and
Not always.
well,
if you're using the recursive
and the standard is always allocating it where you want, so you can have a variant on the stack, even if it's whatever.
Yes, the variant actually holds a row buffer in the size of the largest underlying tab, and
So a
there
union.
it puts all the
Basically, it's a
data
union,
in.
isn't it?
Yes.
It's a union that no
Type safe
where
union.
the enum that we had to implement at the beginning is inside. But discriminate. That's why it's called discriminated. It knows what it's called, unlike the C.
Because it's similar concept in other.
So what overhead on the size, and hold the current type information.
I think it's it's all of the size of the maximal underlying type.
Some additional space.
It has some additional point.
The largest type. It's as large as its largest type.
Plus some maybe two or
Plus some
Yeah,
bytes for
some
alignment.
some
And,
bookkeeping.
Few bits.
8 bytes for alignment.
Actually, with this example, you don't need to use pointers even in the standard variant. Starting from C++17, std vector can hold an incomplete type, and also other containers. So you can forward declare the type and declare a vector to all this type. Since vector is allocating anyway. Yes. Okay, let's just for the sake of completeness continue our game. How many values does this type have? Or the type of this function?
Depends on the other space.
On what?
Function pointer.
No, you mean return values?
How many words?
How
many return types? How many
values of
That's a
ignore this bool, a function which gets a bool and returns a
One.
Four.
How many
One.
one.
Or two.
Four.
Okay,
Then
the
it's two.
correct answer is 4. These are the 4 different functions you can write.
The truth.
Okay, so we said algebraic data type theory doesn't care the details of the implementation of what you did inside this function, but eventually you're going to map the 2 possible inputs to 2 possible outputs.
You ignore side effects that might happen inside the function.
Yes. We are thinking about pure functions.
No exceptions.
Okay, these are the 4 functions in code. Now, how many values? No. Again, you can map each bool to 256 options. So you have 256 options for true, and the same for false. Multiply them. And this function, right, 256 to the power of 3. And eventually,
U to the power of
u to the power of 3. Right. Okay, so we had the product type, sum type, and this, if you want, exponential type. Okay. So this was just for the sake of completeness, and congratulations everyone for completing the game. Again, thanks to Modiin for this whole game. How much time do I have?
Negative number. Out of bounds.
Okay.
10 minutes.
Okay. So let's talk a little bit about polymorphism. Classic example, we have an interface of shape with an area function. We derive two types, square and circle, implement the interface depending on the different shape. Okay, so far classic examples. And to use it, we have to use pointer semantics. So let's say we have one object of type square and one type circle. Then we can insert them to some container. And let's, for example, accumulate using the interface, accumulate the areas, and get the answer. Let's see another approach using variant. So now we first declare the derived types, and they don't need to inherit from anything. And then we collect them using a variant to the generic type. Okay, so shape can be either a square or a circle. Now the functionality. Okay, notice that the types here don't contain their functionality. The functionality is outside. So to implement an area calculation, again we use std visit. Depending on the current type, we compute the answer. And now the usage. Here we can use value semantics. Don't have to use the heap. Okay, we can declare an array of shapes with either a square or a circle, and then use standard algorithms like we studied. Okay, and the same answer as before. If we would like to add a functionality on the classic inheritance technique, we need to add a function to the interface, add an override to each derived type. Okay, and on the variant case, we don't need to touch the types at all. Okay, since as we saw, the functionality is outside the types. We simply can add another function, parameter, which calculates whatever we want.
Which is the point of visitor design pattern.
Yes, that's why it's called std visit. It's the visitor pattern. Adding another type derived type. In the inheritance case, we just add another type derived from the interface, implement the interface. On the variant side, it's a little bit more complicated because we need to declare all the different types and the type of the variant itself. Okay, so where we add, for example, a triangle, we need to modify the variant so it will know it can hold a triangle.
Basically, everything you can do with a variant, you should be able to do with an equivalent inheritance model with 3 derived classes from an empty base class.
Yes, so that's exactly the goal of this.
And it actually makes sense because if you look at variants as the so-called tagged types, where you have some blob and a value, which is a tag, which tells you what to do with the blob. That's exactly what you have with vtables, because you have a vptr, which is also a unique value, which tells you what to do with your data. So it's basically the same.
But the variant is on the free state, the stack. It's not.
Yes.
And it's by the way, it's not obvious that it's how to implement it without any magic or undefined behavior. But that's
okay, and a nice feature of variant is that if we add a type, we need the compiler will shout at us to update each use with a call operator which handles the new type.
Which is also achieved by abstract functions.
If you overload.
no, that's
yes.
If you don't implement an abstract function, the compiler will shout at you.
Yes, you will.
Right. But maybe you have a function outside the interface that deals with this generic type, and you need to update it to deal with new type.
It's a difference. The visitor pattern, it's a trade-off. It prefers adding functionality and not types, and the inheritance, the standard inheritance allows you to add types easily, but not to add functionality easily. That's the trade-off here.
Okay, so
the grouping is different. Localization is different.
yeah, it's two sides for now. Okay, so we had the functionality for the new type. So let's conclude. We have different trade-offs between inheritance model and variant. Basically, variant is better when you know the set of types ahead.
You can just sometimes combine a variant with a variadic template.
What? Again?
Somehow combine a variant with a variadic template. Does have a variant that you don't need to know in advance.
No. You have std_any, which can hold any type.
You can have only one of those in your variant.
I mean, hold an any inside the variant? No, I mean just
no.
hold,
But if you put
just
a variant in a
variadic
variadic template, then at compile time, the compiler will know the entire set of required types.
How it will
just depending on use. Whatever you give it, you instantiate the variadic template with.
You still need to provide the implementation for each type and each visitor.
Okay, that's an interesting idea.
I'm not sure if it's doable or beautiful, but
so when you know the set of types ahead, and I think the biggest thing you gain with the variant is using value semantics, storing things locally, and so basically this is the crux of my talk. If we have a few more minutes, I have some bonus slides.
Amigo.
Okay, I'll make it short. A little bit of gazing into the future. We had the future fortune cookies telling us the future before. Okay, so we saw product types. We have in the language struct and in the library std tuple. Regarding some types, we have variant in the library, but no equivalent language. We have union, but union is flawed. You can't use union with anything that is not default, trivially constructible, instructible. So I disregard it. So there's a proposal by David Senkel to add an L variant, which is simply a language-based variant. This is how, according to the proposal, you would declare it, just like a regular struct, but instead of writing struct or class, you write L variant. So this type can hold either a string or an int, and here you can name the different options what we couldn't do with the library-based variant. Okay, similarly, like tuple and struct. Struct, the members have names, and tuple, they have indexes.
Or types nowadays.
Or using the type as a name. This is the JSON example we saw before, using the L variant proposal. I wonder if we could use just incomplete type here. But since I don't have a compiler which implements it, I couldn't change. Okay, so if today to implement some like a command in a game, we would use this code. This would be the similar code using a language-based variant, much shorter and more expressive.
And then you could have multiple fields with the same type because you have a name.
Yes, you can do this also in the std variant. Have the same types multiple times, but then to get it, you need to use an index. Not the type.
Current compiler doesn't support
Okay. I never saw an issue.
You need to do the trick that you showed earlier, how instruct to each different type.
Okay. So this is the visitation now, and with another thing the proposal is proposing is adding pattern matching. Okay, so it proposes a keyword called expect, and this strange error syntax. So what this code does is pattern match the input to the different types, giving it some name. You can use underscore if you don't care about the name. And this mechanism can be used not only for variants, also for simple enums. Okay, instead of switch, use fact using this arrow notation.
Is there a default case for this?
What?
Is there like a default?
Yes.
No.
I think there is, but I don't remember the
In enum, you need the default.
No, probably called
One
auto.
slide before you.
Maybe it's called auto.
No, with it here it's the current regular switch. Also, you can today, when you want to inspect the contents of some object, you need to use if statements, and with the inspect proposal, will look something like this with this strange at sign. But again, it's still, I don't think it will enter a C++20, so it still has type and chance. Okay, so this says if hit points is 0 and lives is 0, then this. If hit points is 0 and lives is 1, then
Why once with an at? Once with no at? What does the at mean?
at is when you want to use a value and a name. So you, this is the name of the hit points, and this is the value. Okay, that's well.
So